We are Team Liverpool, and this is our project for the 6-point harness buckle design. This is the table of contents. This is our introduction. In this project, we designed, analyzed, and optimized buckles for a 6-point harness. We knew the force exerted, but had to come up with a completely original design for the buckle. The importance of a well-designed buckle is critical to the safety of the driver during a collision. The outcomes for this project are hand calculations that determine the value and location of the maximum stress using stress concentration factors. Conduct a finite element analysis that estimates the value and location of the maximum von Mises stress in the design. An optimized buckle design which meets the safety requirements with the lightest weight possible. Design a buckle that is possible to be manufactured.
These are the assumptions we made when designing our buckle. The forces are at the slot of the buckle and at the hull of the buckle in the opposite direction. The force is distributed equally to each buckle in the harness. The applied force is in tension uniaxially. The buckle material is uniform throughout, or homogeneous. The material of the buckle is assumed to be brittle for hand calculations. The buckle does not experience any moments. The buckle is secured on both of its sides. The fillets on the buckle edges do not affect the stress distribution of the buckle, and the temperature is assumed to be ambient. This is our free body diagram. On the left, we have the force lines that go throughout our buckle design, and on the right, we have the initial dimensions that we have for our buckle. It has a width of 2 inches, a height of 2 inches, and the hole towards the bottom has a diameter of 0.5 inches. The height of the slot is 0.5 inches and the width of the slot is 1 inch. We assume the thickness of the buckle to be 1/4 of an inch. For our knowns, we know the dimensions because we assumed them. We know the material properties. We know the weight of the man was 200 pounds and the force he felt was 100 gravities. And then we know that the gravitational constant is 32.2 feet per second squared. And we knew the ultimate tensile strength was 138,000 psi, and as previously stated, the thickness was 1/4 inch. Our unknowns were the force that was exerted on the buckle, the KT of the hole, the KT of the slot, the nominal stress of the hole, the nominal stress of the slot, the max stress of the hole, the max stress of the slot, the safety factor of our design, and the weight of the design. These are the KT charts we used with our initial dimensions. On the left was for the hole, and on the right was for the slot. These are the calculations we used. For equation 4, that was used to determine KT for the hole, and equation 8 was used to determine the KT of the slot. Equation 4 was also used to determine the slot. On the right, those are areas of a rectangle, circle, ellipse, and triangle, and total area, so that we were able to determine the weight of the buckle. For equations 1, 2, and 3, we used those to determine the force that would go to the buckle. These are our hand calculations. The first step was to determine the force. We determined that the force was 200 pounds multiplied by 100 gravities, and we were able to divide that by the 6 buckles in the harness. So we were able to get a value of 3,333.33 pound force repeating. Next, we determined the max stress at the hole. So first we determined the KT value from the charts. Then we determined the nominal stress and used the area equation from the KT diagram. And from there we got our final answer for the max stress at the hole. Next, we determined the max stress at the slot, and we assumed the plate was an elliptic symmetric hole. We used the same equations from earlier for area and the same equation from earlier for the nominal stress, and then from that we determined our max stress. And since this max stress was higher than the stress at the hole, this would be the max stress of the system. Then we determined the safety factor by dividing our ultimate tensile strength by our max stress, and we got a safety factor of 3.1, which is greater than 1.5. Then we determined the weight by calculating the area of the buckle, and after we determined the total area, we multiplied it by the thickness to determine the volume, and then we multiplied that volume by the density of the material to determine the weight, which ended up being 0.096 pounds.
To optimize the width and thickness of the buckle, we use the equations provided in the course website and plug them into Mathematica to simultaneously solve 7 equations and get the most optimized width and thickness. The width of the buckle should be 1.14 inches, which is about 1 3/16, and the thickness should be 0.149 inches, which is about 3/16. After trial and error using standardized IPS dimensions, we modified our design to meet the safety factor and optimize it to the lightest weight possible. Because of the complexity of the equations, we used Mathematica to solve for the unknowns in a more accurate manner.
These are the graphs we found for KT using the optimized dimensions. The left is for the hole and the right is for the slot. These are our hand calculations using our optimized dimensions that we got. The unknowns and knowns are the same, except our knowns, we already determined the force earlier, so now we have that as a known. But the unknowns, besides the force, are the same. First, we determined the max stress at the hole. We assume a bar in tension with a transverse hole, and we determined the nominal stress after getting the KT from the concentration chart, and then we used the area equation again, and then we found the max stress by multiplying KT and the nominal stress. Next, we determined the max stress at the slot, and we assumed a plate with an elliptic symmetric hole again. Here we used the KT calculations that are given with the diagram, and for D over W and D over A, and then we determined the KT through using the stress concentration chart. We use the same area equation and nominal stress equation from the previous part, and we're able to determine the max stress to be 79.9 KSI. And since this stress was higher than the stress at the hole, it is our max stress for our system. Next, we determine the safety factor by dividing the ultimate tensile stress by our max stress, and we found our safety factor to be 1.73, which is greater than 1.5. Next, we determined our weight, first by calculating the area of our buckle. Then we added the area, and it will determine the total area of the buckle, and then multiplied it by our thickness, which is now 0.1875 inches, and multiplied our volume by our density, and found that our buckle weighed 0.058 pounds.
After trial and error, this was the final dimensions for the most optimized buckle we could create. In SolidWorks 2017, we used the FEA feature, and these are our loads and constraints. The green being the constraints where our buckle would be fixed, and the purple being the loads inside the slot and inside the circular hole.
To place on things. So it's like everything, like when it comes to scales, pitches, and all this other.
In SolidWorks, the mesh can be modified by changing the mesh density. A finer mesh will increase accuracy, but as we can appreciate from the table above, the percent difference is less than 1%. Here we can see the heat map of the von Mises stress, being the max 79.1 KSI, and the min being 263 PSI. As we assumed, where the larger discontinuities were, the larger the stress was. Comparing the FEA, the von Mises stress, to the hand calculations. As you can see, there was not a lot of percent error, and due to the simple geometry of our design, the values had a max error of 18.2, making the hand calculations extremely accurate. Approximately, titanium cost is $18.80 per pound. Already manufactured, it would cost $11.52 per piece. Coming up with a practical manufacturable design that can also withstand the force was the biggest challenge we faced during the design, as well as optimizing the design to make it as efficient and lightweight as possible. We first started with dimensions we believe would work and then optimized our design in relation to the equations that were provided. We then compared the FEAs of the various designs and chose the most efficient. After conducting the hand calculations, we further optimized our design to make it as lightweight as possible and then sent it to the 3D printing lab. SolidWorks has an optimization feature. After viewing the results and reviewing them, you will be asked if you would like to optimize your model. First, you must select the dimension that you want to optimize. Then you can add a constraint, which can be the safety factor, the max stress, or the max displacement. Then add a goal, which can be minimizing the mass. After, SolidWorks will run several situations and select the most optimized depending on your goals and your constraints.